Alright, so this is another example of that are similar to the one that was worked on the homework worksheet C.3.3. So it says if 210 kilocalories, which a kilocalorie is just another measure of energy. It says if 210 kilocalories, which a kilocalorie is equal to that many kilojoules, were added to a 51.5 kilogram sample of liquid water at its boiling point, what fraction of the water would be vaporized? Well, there's actually two ways to solve this problem, but the first way, both ways, I'm going to require that you draw a temperature versus time graph. And so I'm going to sketch it down here in the bottom left. So I have room for everything. I'm going to call that temperature and energy. And then it says, it's talking about this liquid that is at the boiling point. So we know what the boiling point of water is. We know it's at 100 degrees. And does it say anything about changing the temperature? No. So therefore I know that it's flat. The key thing about that is that it's a flat portion. Therefore the flat portion is either going to use the equation Q equals MHF or Q equals MHV. In this case we want to use QHV because we are talking about vaporization or evaporation. And so there's actually two ways to solve this problem. I'll solve one way in blue and then I'll solve the other way in green. So I'm going to call this, I'm going to write out Q is equal to MHV, like that. And so now I start reading the problem again to try and pull out variables. And so I say, okay, if 210 kilocalories, okay, stop. 210 kilocalories, that's the amount of energy that's being pumped in. And so if I could convert that to kilojoules, which should be fairly easy, then that would go in for Q. And so I'm going to convert that down here, and I'll do that in red just so that we can make sure it is distinguished because we'll probably use it for both. And so I'll say 210 kilocalories. I don't know how many kilojoules that is, but I can set up my proportion and say, okay, this is kilojoules. So then I need to say, okay, well, if that's, I need to put kilojoules down here, I need to put kilocalories up here, and 1 kilocalorie equals 4.18 kilojoules. And so then I can just cross multiply and divide, but this is just a simple multiplication. So if I take 210 times 4.18, that's going to give me 877.8 kilojoules. Now I'm going to hold off on sig figs, so don't get all nervous about it. And then I'm just going to take this guy and put it up here. So I'm going to say 877.8 kilojoules is equal to. Now I'm pumping that much energy into system. I know that. And so now I just don't know how much of that mass, and so it says we're added to a 51.5 kilogram sample. The question is all of that sample going to get used up? Well, based on the wording of the problem, probably not, but we're going to find out if it is or not. And so if I'm pumping that much energy, I need to figure out exactly how much mass there is. And so I'm going to just call this M, because I don't know 100%. So then, HV. I know what HV is because it's a constant. It's 2260 joules over grams. Well, now I need to just simply figure this out. Now there's one small thing. If I were to divide these two, there's going to be a little bit of confusion here because it doesn't look like there's going to be much change at all. Now, to maybe make it consistent, if you understand the kilo and everything like that, then don't worry about it. But let's go and change this guy to joules. And so I need to move the decimal 3 spots to the right. So that's 877,800 joules is equal to the mass times 2260 joules over grams. And so then it's just simply a matter of dividing both sides by 2260 joules over grams divided by 2260 joules over grams. So then I just simply take 877,800 divided by 2260. And notice, watch this, the joules cancel, and then the grams, which is in the denominator pops up into the numerator. So therefore, my answer when I divide that is 388.4, and the unit should be grams, and that should be equal to my mass. Now, it asks for what fraction. Well, what fraction is actually going to be very small, if you can see this. Because overall, the amount of total liquid that I had was 51.5 kilograms. But I only vaporized, according to this, I only had enough energy to vaporize 388.4 grams. So to get the fraction, all I need to do is move the decimal 3 spots to the left to make it back into kilograms, 3884 kilograms. And this is the mass that was actually vaporized. And so if I want to find out what fraction of the water would be vaporized, I'd want to take that mass over my 51.5 kilogram. And if I ask you to solve for a percentage, which should have probably been a better question, you take 0.3884 divided by 51.5, then multiply by 100, and you get 0.75%. So less than 1% of the water, 0.75%, less than 1% of the water is actually vaporized. Now there would have been another way to solve the problem, and I'll come over here and work it on in green. The other way to work the problem would start again with the equation Q equals mHV. And again, I know what the HV is. But let's say we don't know what the Q is this time, because we're saying, okay, well I know how much total mass I have. The question now, in the blue, I ask myself, what mass would be vaporized if I donated that much energy? In the green, what I'm asking myself is, well, how much energy is needed to completely vaporize 51.5 kilograms? And so I'm going to call that Q because I'm going to say I don't know that. I'm going to go ahead and change my kilograms to grams just simply by moving the decimal 3 spots to the right. And so that's 51500 grams. Then I'm going to multiply that by the heat of vaporization, which is again that constant, 2260 joules over grams. Notice how my grams cancel real nicely. Ooh, that's 2260. So I'm going to take 2260 times 51500. When I do that, I get a very large number. That's equal to 116390000 joules. That's a lot of energy right there. So now, if I wanted to find out what fraction, I know how much kilojoules there are, and so therefore I'd want to move this 1, 2, 3 to make that into kilojoules, and so now it's 116,390 kilojoules. If I wanted to find what fraction, this is the fraction of energy that's going to actually be used according to the problem. This is how much is required, and so therefore I'd want to take 877.8 kilojoules over 116,390 kilojoules, and so that would be my fraction. If I ask you to solve for a percentage, I just simply take 877.8 divided by 116,390, and again, and multiply it by 100, and again I'm going to get 0.75%. So the moral of the story is, in this problem here, that amount of energy is hardly changing it at all. Only a very small portion of the overall sample is actually being vaporized.